Okay, I would like to give you an example for this. And yeah, he was asking, but he's not here anyway. A very simple example. Let's say a planar 2R mechanism, a 2R open chain. Okay, so we have one joint, the second joint, and we call the joint angles, we call them Q. And you find this in multibody dynamics generally, that the joint parameters, be it the angle or be it a translation, they're called Q, right? So this is normally what you find, and they're called generalized coordinates, right? You have a vector Q that comprises Q1 to Qn and so on, and they are normally called the generalized coordinates. I'm not sure if you are have heard about Lagrange mechanics, Lagrange equations, for example. Yes, you have, yeah. So then you have this notion of generalized coordinates. Anyway, the name doesn't make a difference. So we have two joints, that one, and two links. And on the first link, we affix the F1, and of course, on the second link, we affix the F2. And each of them is supposedly in the middle of the link, which is not indicated. Anyway, I guess this is L1 and this is L2. And the height, just any, here's the space fixed frame. And from there, we measure along, because this is X, Y, Z. So let's call this the height is A and this is B, just any. Okay, and then of course we need the screw coordinates, and we use the screw coordinates relative to the space fixed frame. We call them Y. So first we need the unit vector. So they're all the same because the two joints, the first one, the second one, they're all along the z-axis. If this is the z-axis, so it's 0, 0, 1. Okay, very complicated, right? The y, the little y, is the position vector to a point on the joint axis. Now this is very simple here. I mean, this is to make it really, really simple. I have placed the space fixed frame at the axis of the first joint. That means the distance from the origin to the axis of the first joint is 0. Right? This is that one. Then we have the second joint, this one. The vector, if the vector to a point, I mean, so measured from here, from the origin of of the space fixed frame, to a point on the axis. The axis is like this. This is a joint axis, right? And if the length of this link is L1, then we can say this is maybe here. You could also say any arbitrary displacement, because as I was saying, it could be any point on the axis, right? So the axis goes along this. That's the axis. So you could choose any point on this axis in anywhere, right? But I choose the one that is actually here at the XY plane. But it doesn't make a difference. You could have any. Maybe we see this later on. So, and then that's the only thing you have to do. You have to. So these are the unit vectors. This is still the same. Then we have here the unit vector cross the displacement y. So y1 is 0. That gives 0. And then you take this. The second one is y2 cross e1. I'm sorry. y2 cross e2. You take this cross this, you get this. So the cross product of this vector with this vector is this vector here. Okay. Okay, and then we are almost there, because then you plug it in. Yeah. So what else do we need? By the way, the pitch is 0, right? Because you have roller joints. What else do we need? We need the 0 reference pose of the F1 frame and F2 frame relative to the space fixed frame. Okay. Oh, yep. That's not difficult, because and also to make life easier, I oriented them so that they are initially have the same orientation as the space fixed frame. So the orientation of this and this and this are all the same, which means that initially this is the identity matrix. This is the homogeneous matrix that tells you the absolute reference configuration. So this is the identity, because they are the same rotation. The rotation matrix is the identity. And then, of course, what? The first one is displaced. So we measure from here to here. This is really the initial displacement, right? The vector r. From here to here, you measure what? You measure in x, you measure L half, L1 half. That is here. In y, we measure nothing because there is no displacement in the y direction. And in z, you measure the a. Exactly. So that's it. Yeah, if you write it like this, then it's this. And for the second link, for the second frame on the second link, so the rotation matrix is still the identity. Then, of course, the displacement from here to here along the x is this length, which is L half, and then this is in the middle of the link, so it's L2 half. I'm sorry, what did I say? No, this is L1 plus L2 half, okay? Which is exactly this one. And then the offset in the z direction is b. So we have b, and there's no displacement in the y direction. So that's it. So you have the two matrices. I mean, this is what you get by inspection. This is not nothing to compute, just to read it off the picture or whatever you have, CAD drawing or so. Yeah, and then you plug it in, and then if you do, then you get the displacement. I was actually not preparing this, but I can actually show the computation. I'm sorry. So that was not good. This one. Yeah, because we can also see maybe the computation. And as I was saying, so we have implemented this in Mathematica, but we also have a MATLAB package. I can show you the MATLAB package later, and if you like, you can even you can also use it if you like. This is the basic stuff I showed you yesterday. So essentially, we have defined a function that gives you this Q-symmetric matrix out of a vector, right? That's the opposite. Blah blah blah. We don't need this. Then there is this exponent, this Euler-Rodriguez formula we looked at yesterday. Then we have functions here for elementary rotation by saying that is a rotation about the x-axis, the y-axis, and the z-axis by just plugging in specific axes. Then I have this Q vector, this Q coordinate vector, and this is a function that takes the unit vector, the position on the axis, and the pitch. Yeah, and it does what it does. Okay, and then we have this. We don't need this. That's an important point. The exponential mapping. So the exponential mapping is exactly as you have seen them. Okay, we don't need all this. We need just this part here. Right, so what did we say? We have the P1. I mean, look at the picture. So we said P1 and Y1. The notation is a bit mixed up here. If you want, you can call this Y. And this also. So E1 is 0, 0, 1. So 0, 0, 1. And E2 the same. So Y1, Y2 is, as we said, is 0 and L1. 0, 0. Okay. And then what we get is, of course, the screw coordinate vectors. And this is exactly what we had, what we got from, taking the cost part, because this is exactly what's happening here. Okay, the reference configuration, this is something you have to okay, there we go. Yeah. Okay. So then the reference configuration, that's what we have to specify. This is a function that takes a rotation and a position and plugs it into an SE3 matrix, which is a homogeneous matrix. So this is the identity matrix, and then comes this vector that we just had. Yeah, and then you take the exponential, and then you get, for the first one, for the first joint, you get this. So the exponential that you get when you plug it in for the first joint motion is apparently, so the exponential of this y1 is apparently just a pure rotation, right? Because it's the rotation matrix about the z-axis, and there's no displacement. I mean, no translation. Is that true? I mean, does it make sense? So what I'm saying is that we get out the pure translation, pure rotation, when we plug in this first screw coordinate vector. Mm-hmm. But F1 is here, so if you turn this one, then F would also have a translation, right? But why is it not giving us the translation? Because this is not what it's describing. Again, this exponential, if you say x, anyway, if you say the exponential of y1, what is this? What does this describe? It describes the motion of the copy of this one, right? So and because we are at the rotation axis, it's just a pure rotation. Okay, so how do we get F1? I mean, the proper motion of F1 by pre-multiplying it with A1, and then we get exactly what hopefully is correct. So we get, of course, the rotation, but then we get the displacement in x and y, right? So this again is a homogeneous matrix. This is the rotation matrix, and this is the position vector, and that's the displacement. So you get like L1 half cosine 1 and sine 1, and that should be okay. Maybe not. So in x, we get L1 half, which is exactly this length to here, times cosine the angle. That kind of makes sense, right? And why we get sine, this length times sine of the angle, which is pure trigonometry. So it should be okay. That sounds good. Let's see what we can say about the second one. The second one, I'm sorry. Well, this is this. Shall we look into it? Yeah, maybe maybe just have a look at the exponential of the y2. The exponential of y2 gives you something. Yeah. So first of all, I mean, look at the rotation matrix. It gives you a rotation by the z-axis. That should be okay, I guess, because the second joint again is rotating about the vertical axis, so it gives you this. Now, what is the position part, the translation? That part. That's interesting. Maybe look at the easy one. The y component is minus L1 sine of the angle. So what it gives you is minus L1 sine of the angle. L1 is this, and then times the sine of this angle, and minus. Does it make sense? You say no? Okay, so you mean the formula is not correct. Okay, so I'm looking at this part here, like the y component, minus L1 the sine of Q2. Okay, just remember this one, minus L1 sine of Q2. What does it do? Minus L1 sine Q2. So I'm looking, so this should be the component in this direction. When you turn this joint, and you say it's not correct, I would claim it's correct. Again, what is it doing? What is it doing when you plug in this y2 into the exponential? Correct. So it moves a copy of the space fixed frame. Now, what happens? Okay, the positive rotation angle is like this. Okay. Now, what happens if you turn this to this frame? it does actually go in this direction, minus y, and then it is sine Q2 and times length. I know it's totally confusing. It's a bit strange, right? For the x component, it's L1 minus L1 cosine Q2. So it starts from 0. So it's L1. So you start from here, and then it subtracts actually what happens when you when you turn this, right? So you go a bit further this way, right? And this is exactly what the relative motion is. So it's 1 minus cosine of this times the length of L1. And this is again something I'm not interested in, because I'm not interested in this funny motion. So I'm actually interested in what happens due to the motion of. I'm not sure if it makes sense to look at this one, for example. That's not it. No, we shouldn't maybe not go into. Maybe. I don't know. Yeah, I don't know. It just makes sense to look into this. Of course, what you get, the rotation is easy. So you get the combined rotation, right? So what I'm looking at is now what happens if you combine the motion of the second link and second joint and the first joint. So first of all, what happens to so the first and second? So what happens to this frame, to the orientation of the frame? So you rotate about this and this together. So essentially, you get again a rotation about the z-axis. That's why we have this here, and the angle is the sum of the two angles. Okay. Yeah, you can try to make sense out of this. Maybe just believe it's correct, because in the end, what I'm interested in is this one, the final one, where I multiply this with A2. I mean the reference configuration and the product of exponential. So the rotation stays the same. Yeah, and then we get this. Yeah, but that's easy to explain. Look at this x component, for example. So we have L1 cosine Q1 plus L2 half cosine the sum of the two angles. Okay, so L1 is this one times cosine this angle gives you gives you the x component of this point. Then plus L1 half, this is this one, and now comes additionally the cosine of the Q2 Q plus Q1, the sum of the two angles. So essentially, if you project it down, it's just trigonometry. So you project this length on the x-axis, which is the length times cosine, and then again the length times the cosine. But now the total angle is the sum, so it's L2 half times cosine Q1 Q2, and that's exactly what you get here, and the sign is the same. So it kind of makes sense. It seems to be okay. Good. Very nice. Okay. If this is so, then we can maybe go on and answer your question, because you have been asking. I mean, at least when we talked about this example, you have been asking what the whys are. So first of all, I mean, I keep stressing this. I mean, because all this data that you need, you can easily get from a CAD drawing or from whatever data. And CAD drawings and geometric constructions are much more, I mean, readily available than DH parameters, right? So, and let's see how this goes. This is it. So this is how it goes. Make a bit bigger, I guess. Makes sense. Yeah. Okay. Yeah. What do you need? You need the I don't know. Let's start with the unit vectors. So you need the unit vectors to all these joint axes here. And the space fixed frame is a bit small here, but the green one is here. So I just placed it at the axis of the first joint, but it could be anywhere. Okay, so the unit vectors of the first, second, third, and fourth. No, five. What 1, 2, 3. No, 1, 2, 3. 4, 5. Yeah. So 1, 2, 3, 5. These joints, they all go along the z-axis, right? So we have x, y goes this way, and z goes upward. So they are all pointing along the z-axis. So it's 0, 0, 1 again. So pretty simple. Maybe the other one that is maybe not that simple, but anyway, is this one, and I don't know, was 45 degree or something. I don't know. So the unit vector is like this. Yeah, could be. But anyway, I mean, we had nice examples where you get the funny cat drawing and so on. It looks totally complicated, but in the end, you just measure. I mean, any cat drawing you can measure this, and this is just numbers, and you plug it in. That's it. What else do you need? You need the position vectors. Okay, the y1 is easy because the first axis is actually passing through the origin of the frame. The second one is, this is just what you have to measure. X component is minus d2. Then you go upward. Yeah, 0. Yeah, I go 0. So I take the point actually at this height. You can go upward, but it doesn't make the difference to the screw coordinates. We discussed it yesterday. When you move along the axis, the cross product doesn't change. That was what we had here. If you displace, for example, y along the axis, which means you add here a term with the same vector e, so the cross product cancels out. So you can take any, and that's why I use this one here with the 0 in the z direction. But anything. So then the y3 is here. So you measure d3, yeah, and so on. And so what's this? y5, 4, y4. So 4 is here. So I measure x. Yeah, I'll get confused now. I measure the d4. D4 is here. So d4 is just a point here, and then I measure h4, which is this one, from here to here. Anyway, I mean, this is probably obvious. This is just distances, and there we go. And then you plug this into the formula, and then you get the cross products. I mean, here always the unit vectors, and then you get the cross product, and that's it. So, and then you get finally the exponentials, which I'm not showing because it's not. They're complicated, but in the end, it doesn't tell you anything. You just plug it into the formula. Okay, did this answer anything? Yeah, maybe another example. So what we did here actually is using this formula, right? I was saying this is a nice formula because you need only one reference and everything is expressed the screw coordinates relative to the space fixed frame. But the other option would be to use the body fixed frames. Yeah, that's not what I'm using. Okay, forget about what I'm saying. Now you have this. This is a KUKA robot. No, Stäubli. Anyway, this is an industrial robot from the Stäubli company, the Swiss company. 60-degree freedom robot, and all these measurements you have in the data sheet. You find them there. Yeah, what to say? First joint. So how does it work? You have the first joint is vertical. The second joint goes, maybe here. Second joint, the third joint, the fourth joint is vertical. The fifth is like this, and the sixth is like this. Somehow. Yeah, so which means that if you look at the unit axis of the unit vectors along the axis, 1, 4, 6 go along the z-axis. 1, there's 4, 4, and 6 they go along. The 6, the 4, 5, and 6 they form what's called a wrist, a robotic wrist, because you have this 3-degree of freedom orientation essentially. Because you can rotate here, then you tilt here, and then you have another rotation here. Whereas the first 3 are essentially there to position the wrist. I mean, most of the robots are built like this. They call it wrist partition robots, in the sense that you have a wrist here that does the orientation, and then the first three are essentially there to make the positions. Okay, so yeah, E2, E3, E5, they go along the y-axis, which is this one, because what is it, 2? I mean, this is 2. The joints are here, by the way, right? I mean, I'm not sure if you are familiar with this. These are the gearboxes. This one, that one, this one. This is a bit, yeah, not easy to see. Okay, this is the second joint, third joint axis, the fifth one. I don't know, somewhere here. I don't know. Anyway, and then you have to measure the height, and then again we have just displacement. So what I'm measuring here is the relative displacement between the joints, because this is what you find in a data sheet. And then, of course, when you need the positions of the points on the axis, then you take the y1. It's just having a component in the z direction, z1. The y2, of course, I mean, this goes here, measured from here to here. Yeah, it's z1 plus z12, I guess, right? It's easy. And then the other one is z3. This one here, z3, which is the sum of these. You know, and so on and so on. Yeah, by the way, there is an offset in minus direction in the x, because this is displaced here. So we have a minus x12, for example, for the first one. Yeah, and so on. I mean, yeah, this is just numbers. I mean, you just measure them and so on. And in the end, you have it. And then you do the relative poses, the initial poses, and then in the end, what you get. So this is what I was, okay, and that's it. I mean, it's all the same, and then, you know, you do this. And by the way, the reference positions are actually equal to the position vectors on the joint axis, simply because the frames are actually on the joint axis. This is how they defined it, which is even simpler. Anyway, now the alternative would be to use the body fixed frames, right? So the body fixed frames are indicated here. So this is X, Y, Z, red, blue, green. No, red, green, blue. This is RGB. So X, the Y comes out and Z goes upward. What can I say? Yeah. Again, the unit vector along the screw axis. Yeah, I don't know. Where do we go? Maybe first look at the position vectors. Now, if you use this formulation here, right? You need these co-coordinates expressed in the body fixed frames. The body fixed frames are here. Maybe look at the second joint, for example. Oh, look at the first joint. It doesn't matter. So the first joint, this is the body fixed frame. The first joint is displaced by Z1. So Z1 is here. This is the inertial frame. This is the axis, the joint axis. So we have a displacement Z1. Then the second joint. Okay, now what I forgot to say is, because of the body fixed frames all placed on the joint axes, the displacement vectors are 0 to the points on the joint axis. Yeah, now I'm here looking at the position vectors, because now what you have to do, you have to find the b's. And the b's are the relative poses of this one relative to this one, that one relative to this, and this one relative to this. So the frame I relative to its predecessor, I minus 1. So the positions are, this one is relatively displaced translation along this one, along the z-axis by z1. The second one, that one, goes along the z-axis z2. And at the same time, it goes in the y direction, in the x direction. Now in the y direction like this. And the x direction we can't see because, yeah, because. No, you see it here. You see it here. This is the x direction. This is x2. Yeah, from here to here. You know, I mean, it's just measuring stuff. And it depends on the robot. Sometimes the part is 0 and so on and so on. Yeah, and so then you have it, and then you plug it in, and that's it. There's not much to say, I guess. And they introduced the coordinate frame so that they're all the same orientation. That means the relative orientation between here, and here, and so on is the identity. So that's it. Okay, and then we are there. Yeah, so this is it. And then you plug it in and you get something. Now we come to maybe another example. Last one, maybe. Again, this funny metamorphic hand. By the way, now you see a bit more about the structure, because now this is a cat drawing. This is the 4-finger hand example. And yesterday we had this. There was this question. Now we have what is it then? I don't know. Maybe this is the pointer and this is the middle finger. No, this is anyway. There are 2 fingers here. There's one link. This is the 5-bar mechanism we talked about yesterday. The 5-bar mechanism consists of 1 link, the 2nd link, the 3rd link, the 4th link here, and there's a 5th link here. Okay. Yeah, and so at 1 link we have 2 fingers. At this link we have 1 finger. There's 1 finger here, and there's no finger attached to this link. Yeah. Okay. Yeah. Okay. Anyway, forget about a finger. I'm interested, just as an example, in the palm, the 4-bar mechanism, the spherical 4-bar mechanism. And it's, by the way, it's again a spherical 4-bar mechanism because all the joint axes of the revolute joints, they're intersecting right in this point. Now what you do is, I mean, you can describe the kinematics relative to any frame. I mean, any inertia frame. So you can place it somewhere. I mean, anywhere. For such a mechanism, it makes actually sense to place it at the center of the rotation, at the intersection point. Because when I place my spatial reference frame at this point, what happens is that I mean, first look at the unit axis. I mean, we have unit axis. We have joined the numbered from A, B, C, D, E, whatever. So they go here. These are unit vectors. They go along this way. What would be now the thing is that all the joint axes, they're passing through the origin of the space fixed frame, which means that the displacements are 0, right? Or you could have a displacement vector that would be actually parallel to the axis, so the cross product would vanish. And in this case, it makes it much easier to, I mean, it simplifies the expressions. So that's why I'm doing it, because the screw coordinates, they all have the 0 components here for the translational component, and also the homogeneous matrices, they reduce just to the rotations, and that's it. But yeah, I mean, I just want to point out that in many cases you can deliberately introduce frames. I mean, inertial frame that simplifies the whole stuff. Okay, there we are with this part. Any questions? Maybe I could maybe show you something. So we had this. I don't see anything. Yeah, so we have a MATLAB package. Right. And if you, for example, use the MATLAB package, it's almost the same computations, right? Just the naming is a bit different, maybe. So what you do here is, what do we do here? We have to. How do I get up? Why don't I see this? No. How do I get up in this? Interesting. Okay, that's good. Yep. So there's the code, and then we have the source, and then we have, for example, this. Yep. So we have here all the formulas in MATLAB now implemented. For example, I don't know what. Let's say, what can we do? Screw coordinate, for example, right? So if you look, there is a formula. I mean, there's a function that does the screw coordinates, and now we have the distinction, and maybe this is what I have to still tell you about. So when the pitch is 0, so you know MATLAB, right? So the argument is EPH. So the unit vector, the position vector, and the pitch. And it returns the screw coordinate vector. Okay, so the screw coordinate is E cross product of P and E. If the pitch is 0. I mean, essentially, this is the same. That's the special case of the last one, right? Because the general case was this: you have the vector E, and then comes the cross product P and E plus the pitch times E. Now, the special case here is, what if the pitch is infinite? Yeah. The thing is, I think you haven't been here yesterday when we talked about it. It's more like a convention. I mean, mathematically you can prove it, that it makes sense in the line geometry to have an infinite, to say this must be an infinite pitch. So we have the two extremes: the 0 pitch is a pure rotation. Then there's a finite pitch, of course, which is a screw motion, and then we have an infinite pitch. And an infinite pitch means that you need an infinite translation in order to achieve rotation. So this is, yeah, exactly. A prismatic joint has an infinite pitch, and it's more like saying that you would need an infinite rotation to get, infinite translation to get a rotation, which means you never get a rotation. Yeah. And in this case, the screw coordinate looks different, because then the screw coordinate is just the unit vector. Okay, good. So yeah, this is the function. And of course there are more functions, I mean more sensible functions. For example, the exponential, this is the one that we had. Then there is, I don't know, there is, for example, the SE3 matrix, the homogeneous matrix. Okay, let's go here. Hey. SE3 inverse, maybe. Then you see, this is the matrix, rot post to SE3. We take a rotation matrix, a position vector, and plug it into an homogeneous matrix. That's what you do here, for example. Okay, and so on. What we maybe should do is to look at an example. I should actually be able to somewhere go. Anyway, example, maybe the two planar 2R, the one that we just had, and look at here. So, and what it does is like this. By the way, MATLAB can also do symbolic computations. It's not very, I mean, it works. It's not perfect. For symbolic computation, you better use a different package. Yeah. So, and to make, you know how to do symbolic computation in MATLAB? Yeah. So I say just, we have the parameters L1, LQ, the length, and maybe the joint angles Q1, Q2. And I just say this is a symbolic real number. Anyway, so then we come to the definition of the first joint. So it's P1. Maybe I should make more space here. So essentially it's, so I define B1 and E1, and then I use this function here, and I get exactly what I was expecting. Okay, maybe this is not super interesting. And then we get this one for the second joint. By the way, this is the planar 2R mechanism, right? That we looked at, yeah, this one here. Okay. Yeah. So, and what next? Then we say rotation matrix of the first one is the identity matrix. I mean, they're all identity matrix. So this was this. So here we go. So the identity matrix. Then we have this relative the zero reference position is L1 half and 0A for the first one. This is yeah. I skipped the A anyway. So anyway, you can have the A if you want to. I don't know. Okay, let's have A and let's have B here. Okay, and then you execute it, and then you get yeah. Okay, A and B. Da, da, da. So now we can go here. Oh, there we go. Yeah. So now we have this zero reference pose. Yeah, and then you see, I mean, the vector R is of course defined as I was saying. So, and then we get, what do we get? Yeah, then I have, okay, this is a function that constructs a homogeneous matrix out of the rotation matrices and the position vectors. And then eventually I can use the exponential formula to compute as we did before, right? And remember, this was the funny expression we got. And eventually we get the first, the motion of the first joint, the motion of the first frame, and this is the motion of the second frame due to the joint motion. And this is exactly as we had before. Yeah, I'm not sure if it makes sense to go. I mean, this is simply saying we have the same in MATLAB. You can use it, and you can of course use it for the kinematics and dynamics for the key kinematic chains. This is what we are going to discuss next, I guess. I mean, the velocity. So what have you learned? Have you learned anything? You have seen the description using the product of exponential formula for open kinematic chain, using the exponentials and the screw coordinates for the for lower pair joints. I always use Revolute joints because they're easy to understand, but it works for any of these Revolute joints. Yeah, and there's a package for this, and this is a complete package with all functions, and it also goes to dynamics if you want to. Right, so we need to go and proceed, I guess, to the next part. And the next part is about velocities. That is maybe not so easy because we all have a different notion of velocities and twists and so on. But let's see. Okay, as we said yesterday, there are names for velocities. When you plug the the angular part and the linear part together, they are normally called twist vectors or velocity screws. This is also a term that you find. We need to maybe recall or introduce what we really mean by velocity and how we define velocities. Maybe start here. So how would you introduce an angular velocity? So angular velocity is introduced by looking at the time derivative of the rotation matrix. Does it make sense to you? To you, yes, but I guess other people from electrical engineering, they are not so familiar with this, right? So angular velocity is always something you can discuss for ages and still don't agree on it. So the basic idea is the following. So let's say you have a rotation matrix. And I skipped the zero. So it is R0I, right? So this is giving you the rotation of a frame, of a body, relative to the inertial frame. Now if you take the time derivative of the rotation matrix, that doesn't have a physical meaning. It's just a time derivative. But if you pre-multiply, for example, this time derivative of the rotation matrix with the inverse, that means the transpose of the rotation matrix, then you get something out of it. And this is again a skew-symmetric matrix. Why is it skew-symmetric? I mean, yesterday we introduced this skew-symmetric matrix for a vector, which means that whenever you have a skew-symmetric matrix, there corresponds a vector to this matrix. Yeah, exactly. And one thing, why is actually this, without actually having more knowledge about kinematics, why is this skew-symmetric? What do we know? We know that the rotation matrix is an orthogonal matrix, right? So we know that R transpose times R is the identity matrix. And that's it. That's all I need to know. Then I know that the time derivative, I mean, this term is skew-symmetric. Because when you take the time derivative, okay, the time derivative of a constant matrix, the identity matrix is 0, right? And that's it. So then I'd say, okay, R transposed R dot plus R dot transposed R is 0. And there we go, because then it's almost what we wanted to show, because what we have here is, what's this? This is the so this term, for example, is the same as R transposed R dot transposed, right? Because if you transpose the whole thing, then this goes here and this goes there, and this is transposed and this is transposed. Okay, but that's it. Because what it means, and this is 0, right? So this is 0. On the other way, the other way is saying, if I bring, for example, I don't know which one, this one to the left-hand side, what we get is this is minus R transposed R dot transposed, okay? Which means that this guy is certainly skew-symmetric, because this is the definition. The matrix, so this is the transposed of this matrix. So the transposed of this matrix is the negative of the matrix, which means this is skew-symmetric, okay? So if I know it's skew-symmetric, then I can say, okay, there is a vector that defines the skew-symmetric matrix. Because for any skew-symmetric matrix, there is a vector. Or the other way of saying, any skew-symmetric matrix is defined by a vector. Which means that there is a vector that defines the skew-symmetric matrix. And this vector is giving a name and the physical meaning, and we can show why it has the meaning, which is the angular velocity. So you can take out of this skew-symmetric matrix, you can construct, I mean, let's say like this, and this is of course this is an element of this skew-symmetric matrix space, and you can extract, of course, the vector omega, right, which is a 3 vector. So, and that's it. Because now you have shown, first of all, this is always skew-symmetric. Secondly, because of being skew-symmetric, it's defined, or it defines a vector. And now the vector is exactly the angular velocity. And I call it the angular velocity tensor, whatever. The important point is that this is the angular velocity of the moving frame relative to the space-fixed frame. Okay, the angular velocity of the moving frame relative to the space-fixed frame, but it's a vector. So it must be represented in a certain frame. And it's represented in the moving frame. That's why they call it the body-fixed angular velocity. Yeah, anyway, so the whole thing is the body-fixed representation of the velocity, of the angular velocity and the linear velocity. Now, how do you get the linear velocity of a frame? So I would like to know the velocity of this point relative to the space-fixed frame when I know the position vector. Well, I mean, you can say, okay, this is r dot, right? If Ri is the vector that goes from here to here, then the velocity of this point is r dot. But if I want to express it in the body fixed frame, then what I have to do is simply to transform these coordinates in the body fixed frame. This means multiply it with the corresponding rotation matrix, which is the inverse, that is the transpose of the one that goes from here to here, because we want to go from here to here. Okay, and that's why we have the R transpose times R dot. And so R dot would be the linear velocity represented in a space fixed frame. And this, we call it V now, little v, R transposed, I mean, rotation matrix transposed times R dot, and that's the velocity in the body fixed frame. Of course, the same velocity, just different representations. Now, this is all what you learn in, I don't know, mechanics. The funny thing is, or the good thing, and there is much more theory behind it why this happens, is you can actually define this in one shot by using the homogeneous matrix. Because if you look what happens if you take you kind of copy this idea, right? Because you have the inverse, this is the inverse of the rotation matrix times the time derivative. If you copy this idea and just say, okay, why don't we do the same with the homogeneous matrices? And you take the inverse of the matrix and times the h dot, and you look at what you get. I mean, if you do the math, right, you just take the inverse of h. We know how this works. You take the time derivative. I mean, you just take r dot and r dot, and then you multiply it out. You get exactly this. You get exactly this omega defined like this, and you get the v defined like this. So we can actually say the whole 6 vector consisting of omega and v, which you call the twist or so, right, is defined by this expression. Of course, what we get here is this 4-4 matrix, right? And we have been saying that the 4-4 matrix corresponds to a 6 vector. It's the same like saying the 3 skew-symmetric matrix corresponds to a 3 vector. Now we have the same for the 6 vectors, right? So this screw coordinate vector of the twist, or let's say just the twist, the velocity screw, is defined by this. Okay, much more I don't have to say, I guess. So you have to just have to look into it and digest it a bit. It's no rocket science. It's just the good thing. It's very systematic. First of all, and secondly, having, and this is the point actually, having all expressed in terms of the homogeneous matrices, and knowing that the homogeneous matrices are expressed in terms of exponentials, opens a complete new world of manipulating all these equations and so on. Okay, this is it. There's a different version, which is a bit of a funny version. We're not going to use it. I mean, people in mechanism theory, when you design mechanisms and so on, they use the so-called spatial representation of twists. So see, now we had the body fixed representation of twists, and this is what we're going to use, because now all the angular velocity and linear velocity expressed in the body fixed frame. By the way, why I'm interested in, why would this be better than spatial frame? Because when we go to dynamics, we need to take into account inertial properties of bodies, right? Now, if you express the inertial tensor inertial properties of a body in a body fixed frame, for rigid body, they are constant, right? And it's much easier. If you express the inertial properties in a space fixed frame, they would change all the time, which is true, but it doesn't make sense to. It's just making things complicated without having a benefit. But anyway, just to mention, there is a different version of doing this by just, we had the inverse times the time derivative. What about if you swap it? What if you swap the order, if you take first the time derivative and then the inverse? You can also, with a similar argument, show that they have the same structure. But the thing is, what happens is that, Yeah. So I mean, the angular part, this part is again symmetric. But again, we have this swapping of the rotation matrix. Now, what's the meaning of this? I mean, this is again the angular velocity, but it's the angular velocity of the moving frame relative to the space fixed frame, but now expressed in the space fixed frame. And that is also interesting. And as I was saying, I mean, when you look, when you're always careful with the indices, then you can see this. Unfortunately, I mean, I dropped the zeros, but what you have here is R0I, and you have R0I transposed. Why I'm saying this, because the last index is telling you what comes out of the whole equation. And what comes out of the whole equation is 0. So whatever happens here is expressed in the 0 frame, in the space fixed frame. That's kind of an indication that this is, of course, space fixed angular velocity. What is more kind of mind-boggling or a bit of puzzling you maybe is the linear velocity, because it's the same. I mean, just plug it in. I mean, do the computation, plug this in, and what you get is this, right? So remember this kind of obvious notion of linear velocity by saying, well, I have the r dot, which is kind of, of course, the velocity. I transform it to the body frame, then we have this. What you get here is different. Of course, there's no rotation matrix involved in this because we express everything in the space fixed frame. But then the question is, what is actually the velocity? Of which point is this the velocity? Huh? Yeah, okay. I mean, this equation here, I mean, this expression is the velocity. Of which point? You mean of this frame? No, of this? No. This one? So which point is it? So you're saying this is the linear velocity of the origin of the green frame. So you say of this frame. This is actually, it's actually almost right. First of all, why do you say so? Yeah, okay. But still, a completely change. It's not only the coordinates are different, it's a completely different formula. You're right, actually. It's the velocity of a copy of F0. I mean, of the space fixed frame. But the space fixed frame is not moving. So how could it have a velocity? It's an interesting thing. If you look carefully, you will see that this is actually the velocity of a point that is fixed to the body, because the only thing that is moving here is the body, right? But of a point that is momentarily actually going through the origin of the space fixed frame. So you can imagine that, of course, I mean, regardless of the physical extension of the body, but the body is moving, right? And then you look at, I mean, virtually at the points of the body that is, how to say, of a point that is fixed to the body. Put it the other way. Let's assume this is, I know it's a bit difficult to speak about points that are not part of the body, but let's say the body is bigger, right? And let's say the body is like this, right? So it's moving. So there's one unique point of the body that is at the moment at the origin of the space fixed frame. And this point, the velocity of this point is actually what you're getting out of this equation. Now you can say this is independent of actually being part of the body or not. You can always say, virtually so to say, I have a point attached to the body that is moving with the body, that is momentarily actually coinciding with this origin of the frame. like this is moving somehow, and there's the point that is actually moving with this body and is momentarily coinciding with this frame. And this is actually what you get here, and it's maybe easily understood. So the vector, I mean this vector Ri that goes from here to here. Okay. So let's say look at the last part. So we have the cross product of Ri cross omega. So omega is, I don't know, omega is just the vector with which this is rotating. Let's say like this, I don't know. Okay. Now you take the cross product of this vector r and omega. And what you get is exactly the linear velocity due to this rotation, right? But the body is also translating, not only rotating. That's why you have the change of the vector r. This is r dot. And this together gives you the velocity. And this is the velocity of this point, actually. I mean, of the point in the body that is momentarily coinciding with this point. It's a funny thing, but it has its benefits. And that's why people use it in mechanism theory. Because what could be a benefit? Again, the benefit could be that everything is referred to the space-fixed frame, because you might have multiple bodies, and they're all have velocities, right? Now, you might ask, what is and you might have a chain of these bodies, and you might ask, what is the total velocity of the whole system? You just add them up, right? But normally you cannot just add velocities because they are different, expressed in different frames. The body velocity, for example. If you have multiple bodies, you cannot just add them because you always have to transform the velocities, right, to a common frame. This is here different because they're all expressed in the same frame. You just can add up all these velocities. The interpretation is a bit strange. Anyway, we are not using this. Okay, that's the summary. Not sure how much time we should actually. 5 minutes, because now. Okay, let's start with this. What's the connection between the spatial and the body fixed twist? So the body fixed was defined like this, right? The space fixed like this. And by the way, did I do this? No, I skipped it. In the literature, you find this with the B on top of it for the body fixed. So VB and VB and RB and omega B and little VB and so on. And this with the S. I always skip the B because otherwise we have so many indices and we're always using the body fixed version. That's why I skip it. So we have the VS and the VB, which has no B. So exactly. So we have this one, which you find often with the B. I skip it. Right, this was defined like this: H inverse times H dot, and a space fixed version was defined as H dot H inverse. Okay, fine. What's the connection between them? Well, it's very simple. I mean, you just you multiply. I don't know what you're doing. For example, like here, you what is it then? Yeah, on the left-hand side, you introduce an identity matrix. In a sense that H times H inverse is the identity matrix, right? So I don't make a mistake by doing this. Okay, but what I see is, well, I don't know what I'm seeing. You see that actually in the middle, you get the definition of the body fixed twist. So the space fixed twist is related to the body fixed twist by left and right multiplication with H and H inverse. Okay? Okay. And if you sit down and do the math, because we know exactly how H looks like, right? So H is this rotation matrix and translation vector, and V is this omega tilde, and so on and so on. And if you do the computation, then you see, and if you then extract the vectors, the 6 vectors corresponding to the twist, then you will see that the space fixed twist and the body fixed twist. What is this now? Oh yeah, this is a bit of a derivation, yeah. They are related like this. So the space fixed and the body fixed twist is related by this 6 times 6 matrix. And that's the r and the little r that is in the homogeneous matrix. This matrix is kind of a key in in all the kinematics relations. And there's lots of mathematics going on behind this. This is called the adjoint transformation. Whatever the name is, I mean, you don't have to care. But this kind of transformation matrix is a 6 times 6, of course it must be, a 6 times 6 matrix, because it transforms 6 vectors into 6 vectors, 6 vectors into 6 vectors. So this into this, and has this form. By the way, you could have easily derived this without actually all this. Because the question is, when you transform a twist, like omega v, I'll put it the other way around. If you measure omega and v at a certain frame on the body, how does it change if you change the frame? If you change the frame, exactly. So let's say that you have a So let's say you have one frame here. Oh, that doesn't look nice. Anyway, so let's say that we have a frame, okay, and then you express the velocity and the angular and linear velocity there. Then we have another frame, okay. Let's say this is I don't know, F2 or whatever, and that's F1, for example, right? So, and we have omega here. We have omega expressed in the one frame. And let's say this is so. And what I'm saying is this is all one body. So the whiteboard is floating around and rotating and turning and so on. What's the omega in the two frame? How is this related to this one? I mean, so first of all, omega is a free vector, right? Omega is the same at every point in the body, right? The rotation angular velocity is invariant of the point. The only thing is the frame in which we are representing them. Okay, what we know is that we go from there to there with h, 1, 2, which is, of course, the rotation matrix and I don't have space. Anyway, R1, 2. Oh, no, did like this, R1, 2, 0, 1. Okay, this is our homogeneous matrix. Goes from there to there. Okay, what I know is that, of course, then, how do we get this? Should I say the other way around? We get this by R1, 2, omega 2, right? Sorry, omega 2. Wonderful. Okay, this is not much. What I'm saying is just we have one vector that is invariant from the point, so you just have to transform the coordinates. That's it. What about the linear velocity? That's the most important point. The linear velocity, when we have a vector, because this is the vector R1, 2. Okay. How does the linear velocity, when I have it in the one frame, how does it change to the one in the two frame? And this is where we get some additional terms. Because now you get what? You get, of course, V. Yeah, this should be 1. Sorry. We get, of course, they are the same. I mean, or let's say this is, which one? That one is this one, okay? Plus something that you get due to the offset, right? So the linear velocity here and the linear velocity here is, of course, this one, plus the one that you get due to the offset, which is what? Which is omega cos this distance vector, okay? And if you plug this into a matrix, then you get exactly this, because This part is just saying, okay, this is the distance vector cross omega. So it's essentially the same. So what I'm saying is that you could have derived this without all this kind of twists and so on. Anyway, the message to take is there is a matrix, and this is an important point. When you have, and this is maybe before we go to lunch, the last thing, because this is important actually. So we have two frames, and we have the pose of the two frames. And the transformation is from one to the other with the homogeneous transformation matrix. Okay? That's clear. Mm-hmm. When you transform twists or screw coordinates from F2 to F1, this goes with the what we call now the adjoint matrix of H to 1. And it's called the adjoint because it goes along with this matrix. So there is this point coordinate transformation, and along, so to say, adjoint to the point coordinate transformation goes the transformation with the twist, right? And that is the 6 times 6 matrix. So this is the 4 matrix, and this is the 6 times 6 matrix. Okay, I guess we are ready for lunch. Any questions? Okay, then have a good lunch.